So one section out of chapter 19. Balancing oxidation reduction reactions. And look, I forgot to change that number. Oh well. Okay, so a little review. Redox reactions. What does oil rig stand for? Oxidation is loss of electrons, reduction is gain of electrons. Okay, another way to remember that is oxidation is an increase in the oxidation state, and the reduction is a decrease or a reduction in the oxidation state. Okay, so oxidation state going up or down. Here we're looking at this reaction between calcium and water. We can identify oxidation and reduction by looking at the oxidation states. So here calcium has an oxidation state of 0. Here it has an oxidation state of +2. The oxidation state went up. It's being oxidized. Sometimes, like for a metal here, we can look at the charges and identify whether it lost or gained electrons. To go from no charge to a +2 charge means that calcium atom lost 2 electrons. Oxidation is loss of electrons. When we look at what's happening with the hydrogen and the oxygen in water, wherever there's oxidation, there has to be reduction. We look at this and we're like, you can't just look at the charges, and that's why we have oxidation states. It's a device to help us figure out what's being oxidized and what's being reduced. So the oxidation state of hydrogen here is +2, and over here is 0. So the oxidation state went down. That's a reduction. When we balance these redox reactions, the mass has to balance and the charge has to balance. And sometimes it's pretty much impossible to do that balancing an equation by inspection. And so that's why I'm going to teach you how to do the half reaction method. You take the equation, you break it into 2 pieces, an oxidation and a reduction. You balance each of them separately, then you put them back together again. So reviewing oxidation states. Free elements are going to have an oxidation state of 0. Monatomic ions have an oxidation state equal to their charge. The sum of the oxidation states of all atoms in a compound is 0. In a neutral molecule, it's 0. In a polyatomic ion, it's going to equal the charge on the ion. Oxidation states are like charges, but they are not charges. Metals are always going to have positive oxidation states, and they're going to correspond to their charges. And this is the one that we really need to pay attention to. This is the nonmetals. So this is where we talked about soup. So Fa765, FHO765. Fluorine gets what it wants, then hydrogen, then oxygen, then anything in group 7, group 6, group 5. And what they want is an oxidation state that's equal to the charge they would take as an ion. Okay? So again, it's very closely tied into ion charges. So here's the procedure. And I'll read through this, and it won't make much sense, and we're going to do a bunch of examples. We recommend that you assign oxidation states and identify what's being oxidized and what's being reduced. It's not actually necessary to do that. Then you separate the overall reaction into 2 half reactions. One will be for oxidation, one will be for reduction. You have to separate it into 2 half reactions. You don't necessarily need to identify which one's the oxidation and which one's the reduction. Then you're going to balance each half reaction separately. First, by mass. So balance anything other than hydrogen and oxygen. Make sure that you have the same number of atoms of each kind on each side. Then to balance oxygen, you're going to add water molecules where needed. And after you do that, you're going to balance the hydrogen by adding hydrogen ions. Then you balance with respect to charge. So you look at the charges, and you're going to add electrons. So the sum of the charges on each side of the arrow has to be equal. Sometimes it's 0 on both sides, sometimes it's not, but it needs to be the same. We're looking at redox reactions. So one of them should have electrons on the reactant side, and one should have them on the product side, because we have one's in oxidation, one's reduction. After you've done that, then you have to make sure that you have the same number of electrons in both half reactions, because when you add them together, you want the electrons to go away. You add them together, you cancel the electrons and anything else, and then you double check your work. Okay. So here's our first example. It's a simple example, but that's a good place to start. So I've listed the steps very briefly over here. So let's go ahead and follow all the steps, even though we could skip that first one. So assigning oxidation states. We'll do that as a review because that could definitely show up in the final exam. Aluminum, solid, what's the oxidation state? 0. Copper 2+ ion, +2. How about aluminum 3+ ion? +3, and copper solid, 0. Okay, so we see that the aluminum is going from 0 to +3, that's an oxidation, and the copper is going from +2 to 0, that's a reduction. So we're going to have two half reactions. I like to just take the first reactant and start with that one. I really don't care what order they're in. So aluminum is going to aluminum 3+. We cannot transform aluminum into copper. It just doesn't happen. It'd be fun, but we can't. And then the other reactant, copper 2+ ion, is going to copper solid, the element. So we're going to use all of these up here, but we're splitting in them into two equations. Any questions about that? So then we balance by mass. 1 aluminum, 1 aluminum. Done. 1 copper, 1 copper. Done. Okay. Then we have to do charges. So here on the left side, there's 0 charge. On the right side, there's a +3 charge. I need to make them the same, and I'm going to do so by adding negative electrons. So if I add 3 electrons to this side, 3 positives and 3 negatives add up to 0, and that's the same as what's on the other side. And that makes sense because this is an oxidation reaction, and oxidation is loss of electrons, so it's losing those, it's giving them up. What do I need to do to the second one to balance it? Add 2 electrons on the reactant side. So 2 electrons, and this positive 2 charge adds up to 0, and this side is 0. Any questions? So what's happening here is the aluminum, as it's going to aluminum ion, is releasing 3 electrons. When a copper ion goes to solid copper, it takes 2 electrons. So we can't just put these two together because then we're going to have 1 electron going nowhere. That can't happen. That's why we have to multiply, make sure that these numbers are the same. 3 and 2 are not the same. But if I multiply this top reaction by 2, what do I get? How many electrons? 6. That's not what I meant to do. If I multiply by 2, I'm going to get 6. If it's going to stay balanced, though, I have to multiply everything by 2. All the coefficients. Okay with that? What should I multiply the second equation by? To get 6 electrons. 3. It's not that I'm trying to get 6 on each side, it's that I'm trying to get the same number on each side. 6 is the lowest common multiple of 3 and 2, if you speak math. Actually, it is even if you don't speak math, but okay. Now we can add these two equations together. Now we see that this half reaction released 6 electrons, and those 6 electrons went into the second reaction. So those electrons just transferred from one thing to another. They don't show up as a reactant or as a product. And so we're just going to cross them off. They got made and used up. And then we're going to write down everything else. So we've got 2 aluminum atoms plus 3 copper ions. And that's going to make 2 aluminum ions and 3 copper atoms. This top equation was mass balanced, right? But it wasn't charge balanced. There was a positive 2 charge on the left and a positive 3 on the right. Charges don't appear and disappear out of nowhere. When we look at our balanced equation now, we've got plus 6 on the left and plus 6 on the right. And so we don't have charge appearing or disappearing. Any questions? Let's do another one. Hydrogen ion plus chromium gives hydrogen gas and chromium ion. What are the 2 pairs here? What should I pair up hydrogen ion with? The H2, right? Those 2 must go together. And the chromium ion must go together, right? So do I have to do oxidation states? No, I don't. You do need to know how to do it. So hydrogen ion is going to make hydrogen gas, and chromium is going to make chromium 2 ion. Any questions? Balance with respect to mass. Well, there's no other elements besides hydrogen, so we'll just do the hydrogens. There's 2 hydrogens here, and there's only 1 there. So if I put a coefficient of 2 in front of H+, then I've got the right number. And the second equation is already balanced with respect to mass. And now I need to balance with respect to charge. So here I've got 2 plus on the left and 0 on the right. So if I add 2 electrons here, that'll give me 0 on both sides. What do I need to do to the one on the bottom? Add 2 electrons on the product side. So that 2 negatives and 2 positives, this side adds up to 0, and that side adds up to 0. Okay? Then we check, are the numbers of electrons the same? Oh, cool, they are this time. So we add them together, cancel out the electrons. There's nothing else that's common on both sides. So we just rewrite this. 2H plus Cr solid going to H2 gas plus Cr2 plus aqueous. Any questions? Yes?
Why not just 1 electron, so it's just 2 electrons plus 2H+?
Why 2 electrons here instead of 1?
Okay, let me rephrase that real quick. Why did you put the 2 next to the H+ and then the 2 electrons?
Okay, why did I put this 2 here in the first place? Because before that I had 1 hydrogen atom here, and this is H2, a molecule containing 2 hydrogen atoms. And so I have to have the same number of hydrogen atoms on each side. I can't change the formula, H+, I can just change the number of those that I have. So it's 2 hydrogen ions are combining to form 1 molecule containing 2 hydrogen atoms. Any other questions? Okay, let's do another one. Let's do the charges on this one. I mean, not the charges, the oxidation states. What's the oxidation state of Fe2+? Plus 2. What do we do with, that's permanganate ion, if you've forgotten.
Just ignore it.
Just ignore it. We can do that. Okay, what's the charge on, or oxidation state of iron 3? 3 plus. And how about this manganese 2 plus?
2.
Plus 2. Okay, so we ignored the MnO4. We got to come back to it. So this is a polyatomic ion. it overall has a -1 charge. That means that the oxidation states of the 4 oxygens and the 1 manganese have to add up to -1. We don't know what manganese is doing here, but we know what oxygen wants to be. Oxygen wants to be -2. So oxygen's -2, and there's 4 of them. So that's a total of -8. And we know that all of this has to add up to -1. So what is the oxidation state for the manganese? +7. That seems like kind of a high number, doesn't it? But manganese does that. It's okay.
What happens to the oxygen in the product side?
That's an excellent question. What happens to the oxygen? This would be hard to balance by inspection because there's no oxygen on the right side. The half reaction method is going to help us out. So do you have to find this as +7 to balance this? No, you don't. But on the final exam, if they ask you what the oxidation state of manganese in permanganate ion is, now you know what to do. Okay, so we need 2 half reactions.
The oxygen's supposed to be -8, by the way.
Each oxygen's -2.
Oh, so you're just going to put the -2 there?
Yeah, you just look at the individual atoms.
Okay.
Yep. So we've got iron 2 going to iron 3. That's looking kind of simple there. And then we've got this more problematic one, permanganate ion going to manganese ion. So we balance with respect to mass first. So 1 iron and 1 iron. Well, that was easy. 1 manganese, 1 manganese. That also was easy. 4 oxygens, no oxygens. We can't just throw a coefficient in here. The directions say balance the oxygen by adding water molecules. This is a reaction that's happening in aqueous solution. There is water everywhere. So I can add H2O over here, and that's fine. So there's 4 oxygens, so I need 4 water molecules. So that's what happened to the oxygen. Yeah, now I've thrown in hydrogens that weren't there and made a new problem. You balance the hydrogens by adding hydrogen ions. So over here, 4 times 2, I have 8 hydrogens in the water molecules. So I need to add 8 hydrogen ions over here. Now I've got the right number of atoms of each element. Any questions? Why? Why do we do it in this way is because it's the easiest way. There is water present. Water dissociates into hydroxide ions and hydrogen ions. So in any aqueous solution, there is as much water and as much hydrogen ions or hydroxide ions as you might need for your reaction. So it's not like we're just making stuff up or throwing things in that aren't there. They are there. It's just usually we assume that the water's not participating in the reaction, but sometimes it is. So now that we've got it mass balanced, we balance for charge. So the top one, +2 on this side, +3 on this side. I need 1 electron, and I need to put it over here because this +2, +3, that's a 3. +3 and 1 negative charge. That adds up to -2. Oh, good grief. Anyway, adds up to +2. This side's +2, and this side's +2. They're not both 0. That's okay. They just need to be the same. This one's a little more complicated. Over here, I've got a total of +2. And, you know, if you start getting lost in that, go ahead and write notes for yourself. Here I've got 8 +1 charges, so I've got a +8, and this is a -1 charge, so 8 minus 1 is 7. So I got +7 and +2. So if I add 5 electrons, so Then I've got another -5, and now I've got +2 on both sides. Okay? The math isn't hard, but it can make your brain hurt thinking about it. So you balance the charges by adding electrons. What do we need to do next? What needs to be the same? Number of electrons on both sides. So this half reaction has 5 electrons, and this has 1. So the lowest common multiple would be 5. So if I multiply all the coefficients in this first half reaction by 5, it's still balanced. But now this 5 electrons matches this 5 electrons. If you're trying to balance an equation like this, you can't necessarily see what the electrons are doing. We know that the electrons are doing something. It's an oxidation-reduction reaction. But it's hard to tell exactly where they're going, exactly what they're doing. By pulling it apart into 2 half reactions, we can account for the electrons. So now that we've got them the same, we add them together, we cross off the electrons. And always a good idea to look for other things that might be the same. There's nothing the same on both sides. It's a little bit like crossing out spectator ions. So we've got 8 hydrogen ions plus 1 permanganate ion plus 5 iron 2 ions. And that's going to make 5 iron 3 ions and a manganese ion and 4 water molecules. Any questions? Definitely silent. Let's do another one. There's a bunch of them. You'll thank me later. So here we have copper and nitrate ion, and we're getting copper ion and NO2. So we can just do, we can go, we could if I knew what I was doing. I don't want to do that. There we are. So is the copper going to turn into copper ion or nitrogen dioxide? Copper ion. And then the nitrate is going to turn into NO2. It was looking like an L to me. That's a G. Good, because NO2 is not a liquid. First balanced by mass, 1 copper, 1 copper, 1 nitrogen, 1 nitrogen, 3 oxygens, 2 oxygens. To balance the oxygens, we're going to add water as needed. I've got 3 oxygens here and 3 on that side.
You can just add water whenever you want.
You can just add water because it's all dissolved in water anyway. There is a vast excess of water. So it's not like we're putting water in a dry thing that didn't have any water. Now we have to balance the hydrogens. We balance the hydrogens by adding hydrogen ions. So we need 2 hydrogen ions to give us 2 hydrogens on this side and 2 hydrogens on that side. Then we balance charges. Here I've got 0 on the left, +2 on the right. I want to make them the same by adding negative charges. So I need 2 electrons here. Down here I have neutral things on the right, so that side is 0, and over here I've got +2 and a -1, so that overall is +1. So I only need 1 electron over there to have the same charge on each side of the arrow. Then we need to make the number of electrons the same. Well, the first half reaction has 2 electrons, the second only has 1. So we're going to multiply all the coefficients here by 2. Okay? 2 electrons, 2 electrons. So I can add these together. Those are going to go away. The 2 electrons produced by the first half reaction get used up by the second half reaction. They do not show up in the overall reaction. So I've got 4 hydrogen ions and 2 nitrate ions. And just like adding in math, the order in which you put these doesn't matter. If you put the copper in there first, it's fine. A master in chemistry actually doesn't care either. I know it can be stupid sometimes, but other times it's pretty with it. Any questions? So these have all been examples of balancing a redox equation in acidic solution. An acidic solution has acid in it. What do acids release when they dissolve in water? No, hydrogen ions, right? An acid is something that releases hydrogen ions when dissolved in water. So that's why we've got hydrogen ions in our equation. They may be on the reactant side, they may be on the product side, but this is an acidic solution. What if it's a basic solution, though? In a basic solution, there's really no hydrogen ions present, not a significant number. What do we do? Well, this is what we do. We add one step. When you're balancing each of the half reactions by mass, you balance everything but hydrogen and oxygen. You balance the oxygen by adding water. You balance the hydrogen by adding hydrogen ion. And then because it's a basic solution where we have hydroxide ions, we're going to neutralize the hydrogen ions that we put in there by adding the same number of hydroxide ions. And we're going to add that to both sides of the equation, so it's not going to mess up the balancing that we just did. So if I have a hydrogen ion and I put a hydroxide ion in there, what are those going to combine to form?
H2O.
H2O. So if I had 2 hydrogen ions and I want to get them out of my equation because it's a basic solution, I'm going to add 2 hydroxide ions and I'm going to end up with 2 molecules of water. Okay? Examples. Balance this reaction in basic solution. So we see basic solution, we just kind of tuck that in the back of our minds. We'll deal with that later. Half reactions. So you've got I minus, aqueous. And what's that going to go to? I2. If you try to make the I minus into MnO2, you're going to have a really tough time. And then the permanganate ion goes to the MnO2. Balance for mass. So we have 1 I and 2 I's. So I need a coefficient of 2 there. So I've got 2 I's on each side. Down here, we do things other than oxygen and hydrogen first. So manganese, 1 manganese and 1 manganese. We're good. Oxygens, we got 4 on this side and 2 on that side. So I need to add 2 water molecules. So the oxygens are balanced. But now I've introduced hydrogen in there, so I have to balance the hydrogen. I have 4 hydrogens on this side, so I'm going to put 4 hydrogen ions on the other side. Now we've got everything balanced, but it's a basic solution. So instead of having hydrogen ions, we should have hydroxide ions in our equation. So we look at the hydrogen ions, and we're going to add the same number of hydroxide ions. This was balanced, though, and so we can't mess it up. We need to add the hydroxide to both sides. If you do the same thing to both sides, it doesn't mess it up. So 4 hydroxide ions on that side. I was trying to avoid this, but I didn't succeed. 4 hydroxide ions on that side. I'm just going to leave off the AQ because I ran out of space. Any questions? I think it's easier to kind of simplify things a little bit here. It makes the counting up of charges easier. 4 hydroxide ions and 4 hydrogen ions make what? 4 water molecules, right? So I'm going to erase those and write the 4 water molecules instead. Is it still balanced? Yeah. We haven't fixed the charges yet, but it's still balanced in terms of mass. Now, I've got 4 water molecules over here, and I've got 2 over there. I could take 2 out, couldn't I? Do you want to look at that now, or do you want to look at that later? Now. Okay, thank you. Someone has to tell. So 4 water molecules and 2 on the other side. If I subtract 2 water molecules from each side, doing the same thing to both sides, it's still balanced, right? So I'm going to change this from a 4 to a 2. And I'm going to get rid of these 2. You can count up the H's and the O's and the MN's, and it's still balanced. Now we need electrons to balance the charges. In this top equation, half reaction, I've got 2 negative charges over here, and I've got 0 over there. So I'm going to add 2 electrons over here. So the charges are the same on each side. Down here, I've got a -1 charge on the left and -4 on the right. So I have to add 3 electrons to this one. Okay. Then we need to get the numbers of electrons the same. And we got 3 and 2 again. So the solution to that is 6. So I'm going to multiply everything down here by 2. So I've got 6 electrons in the bottom. The top one I have to multiply by 3. Okay? Now I can add them together and have the electrons cancel out. Because I've got 6 electrons and 6 electrons. So I've got 2, no, 6 I minus plus 4 water molecules plus 2 permanganate ions, and that's going to form 2 MnO2 and 3 I2, no, AQ, and 8 hydroxide ions. Add up the charges on each side, add up the numbers of elements on each side, double check that it's balanced. Any questions? Is this the last one? Oh, this is the last one. Last one! Last PowerPoint slide of the semester. Woohoo! Balance this one in basic solution. So yesterday someone asked me, well, how do we know that it's in basic solution? Well, you know because they tell you in the question. That's the only way you'd know. Has to be acidic or basic, and they have to tell you. So that's not so bad. Okay, so ClO minus aqueous. We split into half reactions, and that must be the Cl minus on this side. And then we've got this guy. It's a complex ion that you will learn to name in Chem 1B. And that's making chromate ion. Do the first half reaction. Everything, balance things other than hydrogen and oxygen first. So one chlorine, one chlorine. This side has one oxygen, the other side has none. Add water. Just add water. It's like instant something. So now the oxygens are balanced, but we introduced hydrogen, and so we have to add hydrogen to the other side.
We don't do hydroxide because...
We don't do hydroxide at this point because you can try that on your own. It gets ugly fast. It's actually...
I thought since it's a basic one...
Right. We will have to add hydroxides, but you need to add the hydrogen ions first.
Hydrogen first.
Because that tells you how many hydroxides. How will you know what? Because that's what the directions told you to do. Balance as if it were acidic first. And the reason is, so if I'm trying to balance these hydrogens and I'm using hydrogen ions, the hydrogen ions don't have any oxygens with them. So I'm not going to mess anything else up. If I try to balance hydrogens by adding hydroxide ions, then I'm also messing up the oxygen, and you're going to go in circles and get really frustrated. So we do it this way. Everything's balanced. Now this tells us how many hydroxide ions we need. It's the same number as there are hydrogen ions. So there are 2 hydrogen ions. Because it's basic solution, we're going to add 2 hydroxide ions to both sides. And then 2 hydroxides and 2 hydrogen ions make 2 water molecules. This is best done in pencil, by the way. 2H2O.
Could we just done that from the beginning? Or I guess you had to see how many.
You had to see how many hydrogen ions there were. After you do this a lot, you can kind of do some of these steps in your head, but you still go through the same steps. And then if we want to simplify even more, we can say, well, here's a water molecule and there's 2 water molecules. I could get rid of 1 on each side. This time I'm going to just leave them for the end. We'll figure it out later. So that's the first half reaction, balanced for mass. Second half reaction, 1 chromium, 1 chromium. 4 oxygens, 4 oxygens. So far, so good. 4 hydrogens, no hydrogens. So we add 4 hydrogen ions. It's balanced with respect to mass, but it's supposed to be a basic solution. So we look at the number of hydrogen ions and we add the same number of hydroxide ions to both sides. It's still balanced with respect to mass. Then I look at these guys over here and I say, well, you put all those together, that's going to be 4 water molecules. So everything's balanced with respect to mass. Now we do the electrons. First half reaction, 0 and -1. So we've got a total of -1 on this side and -1 and 2 more negatives, so a total of -3 on that side. So I need to add how many electrons on the left? 2. 2 electrons. So I've got 3 negative on the left and 3 negative on the right. Down here I have 4 minus charges and 1 minus charge. So that's a total of -5. Over here, I have -2. I need to add electrons to make it -5, so I need 3 electrons. Begin with the 3 and 2 thing. So the next step is getting the number of electrons to be the same. I've got 2 on one of these and 3 in the other, so I'm going to make them both be 6. I get 2 to be 6 by multiplying by 3, so I have to multiply everything by 3. I know, it's rough.
Oh, wait, isn't that one? 3. CLO minus 3 is 3. You just got happy with the 6s.
I did get happy with the 6s. I was checking to see if you're awake.
Very.
That's good, because I'm not. That should be a 3. I did this worse yesterday. We're multiplying by 3 to get 6. This will get us 6.
There we multiply by 2 in the bottom.
Yep, multiply by 2 in the bottom. Let's see if I can do that. So that'll be 8 times 2 times 2 times 2 times 2. Phew. It's getting warmer in here. So we can cross off the electrons. We'll always be crossing off the electrons because we're setting it up that way. Okay. Let's look and see if there are any other things that are the same on both sides. Are there? Yeah. We have water molecules on both sides, and we have hydroxide ions on both sides. So we can deal with them by crossing things out up here, or we can add them all together and then deal with it. Since they're all over the place, I'm just going to add them together and then deal with it. So we've got 8 hydroxides and 2 of those guys. And 3 hypochlorite ions. And 3 chloride ions.
You're going to miss the water.
I did miss the water, thank you.
Yay,
Yeah, sorry, I can recover from that.
That would have sucked if you lost all this.
Oh, it's happened before. It's happened before. That's what forward and back are good for. You know, I did want to get rid of that. Okay, yeah, I left the water out. That's no good. It's a drought, right? Oh, wait, we're not in a drought
Actually,
anymore.
yeah, officially we're out of it.
Officially, yeah. We'll see. Okay, I can tell I'm not going to have enough room to write all of that mess over here, so I'm going to just go down and kind of indent that and write it down here. So 3 chloride and 3 H2Os and 6 hydroxide ions and 2 chromate ions and 8 water molecules. Did I forget anything?
No.
No? Okay. So we see that there are 8 hydroxide ions on the left and 6 on the right. That's just kind of messy, right? So we want to take the same number away from both sides. So I can take 6 out. I can get rid of all 6 of those and knock this down to 2 hydroxides.
Do the same with the water.
And I can do the same with the water. Here I've got 6 water molecules and 8 water molecules. I can get rid of these 6 here and cut this down to 2. And then you may want to rewrite that again. Wait a minute. I screwed up. What else is going funky in there that I forgot to do? There's 3 waters here and 2 over there. Oh, man. But I did already cross out all of those. So I just need to combine these together. So I've got 2 and I've got 3, and so I'll move these over and it should be 5. You cannot balance these in your head. You have to write stuff down. Any questions? Isn't this fun?